In this video, we're going to continue with our differentiation rules, and we're going to start with something called the product rule. So if u and v are differentiable at x, then so is their product. And moreover, the rule here is the derivative with respect to x of our function u times v is equal to the function u times the derivative of v with respect to x plus the function v times the derivative of u with respect to x. And we're going to go ahead and prove that now. We're going to prove that now. So here is our proof. Let's leave that down. So the derivative with respect to x of u times v is equal to the limit as h goes to 0 of u of x plus h times v of x plus h. Ignore that line, please. Minus u of x times v of x. And all of this is divided by h. Now we're going to do something a little strange. We're going to introduce a term that's going to help us separate our limit into limits that become a derivative of either u or v. So here's how we do that. Well, first we just still have the limit as h goes to 0. We have u of x plus h v. I did it again. V of x plus h, so u of x plus h times v of x plus h. And here's what we're going to do. We're going to add and subtract the same term. So here's a little trick we can do. We're going to add, or subtract in this case, u of x plus h times v of x. But we're going to add that same term, u of x plus h times v of, I did it again, v of x. Okay, so really we're just adding 0 here. So this is completely allowed. And we'll see why this is useful in just a minute. But then we still have our minus u of x times v of x here, all divided by h. Now let's separate all of this. So we have the limit as h goes to 0 of several things here. First, in this right here, we have a u of x plus h in both of these terms up here. So let's factor out a u of x plus h. And then what's left over is we get v of x plus h minus v of x, all divided by h, right? We're just taking this fraction right here. Right? We can separate this. We can have this fraction divided by h plus this thing divided by h. So that's what we're doing. And then out of this first one, we factor out a u of x plus h. And then over here, we have the other one. But here we have a v of x in both, so we're going to factor out a v of x. So we get a factor out of a v of x out of both of these, and then we're left with u of x plus h minus u of x all over h. All right. Well, what is this? We're taking the limit as h goes to 0 of a sum and then some products in there, so we can separate this and take the limit as h goes to 0 of u of x plus h times the limit as h goes to 0 of v of x plus h minus v of x all over h, plus the limit as h goes to 0 of v of x times the limit as h goes to 0 of u of x plus h minus u of x all over h. Okay. Well, what is this? How do we figure out what this is right here? Well, we were given, right? Let's go back up here and look at our assumptions. We're given that u and v are differentiable. Well, if we recall from videos from a previous week that if u is differentiable, it is also continuous. So u is a continuous function. If that is the case, that means that the limit as h goes to 0 of u of x plus h is just, our definition of continuous is when we see an h here, we can just plug that in, so of what that is. So h is 0 here, so this is u of x plus 0, which is just u of x. Oops. Okay, so since u is a continuous function, we get this, and that is that the limit as h goes to 0 of u of x plus h is just u of x. So this is u of x times, and then what is this? Hey, that's our definition of the derivative of v. And again, we were told v is differentiable, so we do have a derivative. So this limit does exist, does in fact exist. And that is just the derivative of v. Okay, and then we have plus the limit as h goes to 0 of v of x. There is no h here, so essentially we treat that as a constant. The derivative as h goes to 0 of a constant is just that constant, so v of x. Times the limit as h goes to 0 of u of x plus h minus u of x over h. Well, that is again our limit definition of the derivative of u. So we get u of x times dv dx plus v of x du dx, which is exactly what we wanted to prove the derivative of this product was. So we are done. And that is our proof there. Now, let's think about that via a picture just to see what's going on. We have some function u of x here and some function v of x here. And then we add some change in u of x, and we add some change in v of x, right? This little triangle means change in, just as a reminder. So you have some change in v of x and change in u of x. This change is given by an increase in x, right? As we add some h, if we add h to the independent variable in here, then we're going to get some change in u of x, and we'll also get some change in v of x. So what we want to do is we have the product of v of x and u of x here, right? That would be this region. And we want to ask that if we ask what the change in u of x times v of x is if we add h in the horizontal direction, so in our independent variable. Well, let's think about what that is. What is our change here on this product? That's our question. What is the change in our product? Well, as h goes to 0, this change in u of x is very, very small. So what do we get here in this region? We actually get v of x, right? How do we find the area of this rectangle here? That is the height times the width. Well, the height is v of x times our change in u of x, which, what is the change in u of x here, right? That is essentially our derivative of u with respect to x, right? Because we're asking what the change in u is as we do a small change in the variable x. Similarly, up here, this is going to be u of x times the change in v of x. Which, what is that? That is essentially u of x times the derivative of v. And what is this region here? Well, here we get a change in u of x times the change in v of x, but these are two numbers that are approaching 0, so this goes to 0 as h goes to 0. So what is our change in this product, u of x times v of x? Well, the change is this region right here plus this region right here. And what are those two things? Well, those are v of x times du dx and u of x times dv dx. So we get the sum of those two things. So if we look at the picture, we should expect that this was the answer. So I just drew out this picture to help us intuitively see why we believe this should have been the case, but we worked out the proof analytically here anyways. So the picture was just to help with a bit of intuition on why this ends up being our solution to our product rule. All right. And that is our product rule. We'll look at an example in just a few minutes, but first I want to write out what our quotient rule is. I am not going to prove this one, but we'll write out what our quotient rule is, and that is that if u and v are differentiable at x, and if the denominator, v of x, does not equal 0, then the quotient, u over v, is differentiable. And furthermore, the derivative with respect to x of u over v is v du dx minus u dv dx all over v squared. And this is our quotient rule. So, all right, what is this? That is the denominator, the function of the denominator, times the derivative of the function in the numerator, minus the numerator times the derivative of the denominator all over the denominator squared. You need to absolutely remember the ordering here. It is very different if you do u dv dx minus v du dx, right? That would be, in fact, the negative of what the correct answer is. So make sure you get your ordering correct here. It is the denominator times the derivative of the numerator first, and then subtract the numerator times the derivative of the denominator. Again, I'm not going to prove that. You'll just want to memorize that. There are a few mnemonic devices that can help with that. You can look that up if you need to, but just find some way to memorize this formula. Okay, and the last thing in this video is we'll just do a couple of examples. So we're going to find f prime of x when, and a here will be, how about we do x cubed plus 2x squared minus 4x plus 1 times x squared plus 2x minus 7. What if we want to do that? Now, what we could do is we could multiply these things out and then take the derivative once we just have a longer polynomial, right? In our previous video, we would have known how to take the derivative of that. But instead of doing that, how about we use our product rule? So we have two functions multiplied together. So to take the derivative, it is not the derivative of each of these separately. We must use the product rule. Okay? Which, what does that mean? If this is our function f of x, then f prime of x is, let's call this u of x and v of x. F prime of x is u of x times the derivative of v, so v prime of x, plus v of x times the derivative of u, so that's u prime of x. So let's go ahead and see what that is. All right, we write in u of x here. All right, that's just x cubed plus 2x squared minus 4x plus 1. And then we need to multiply that by the derivative of v. Well, what's the derivative of v? Derivative of x squared is 2x. The derivative of 2x is 2. And the derivative of a constant negative 7 is just 0. Then we add this to v of x, which is x squared plus 2x minus 7, times the derivative of u, so u prime. Well, what's the derivative of u here? Derivative of x cubed is 3x squared. Derivative of 2x squared is plus 4x. The derivative of negative 4x is negative 4. And derivative of 1 is 0. So we're done. And this is our derivative. No need to multiply all of this out in the end. That's a lot of extra work that is not necessary. So leave it in this form. If you did choose to multiply these out in the first place and then take the derivative, then you would need to multiply all this out and add and combine like terms to confirm that these were in fact equal. But we had already proved that this is our rule, so we don't need to do that. We just use our rule each time. Awesome. So we have one more example here, and that is going to be to do an example using the quotient rule. How about we do the same one? But instead of multiplying those functions, let's divide them. So let's suppose f of x is x cubed plus 2x squared minus 4x plus 1 divided by x squared plus 2x minus 7. Let's do the derivative of this. Well, our derivative rule here is d dx of u over v was v du dx minus u dv dx, all divided by v squared, so the denominator squared. Let's go ahead and just use that rule. Okay, so we write the denominator first. So that is x squared plus 2x minus 7 times the derivative of the numerator. Derivative of the numerator here we already did. That's 3x squared plus 4x minus 4. Then we subtract u, so the numerator, that is x cubed plus 2x squared minus 4x plus 1, times the derivative of the denominator. So what is that? Well, that is 2x plus 2. And then we take all of that and divide by the denominator squared. So that's x squared plus 2x minus 7, quantity squared. And again, don't reduce this. Leave that as it is. Circle your answer and be done. All right. And that finishes out this video.